Force on a current carrying wire. For each case below, determine the magnitude and direction of any magnetic force on the wire. In each case, assume that the length of the wire that is in the B field is 1.5 meters. L, we are assuming in every single case, is 1.5 meters. And whenever we want to find the magnetic force on a wire that's carrying a current within an external magnetic field, the equation that we want is IL cross B, which means that the magnitude of FB is going to be given by FB is going to be I times L times B. And then how do we remember if it's sine or cosine? We remember that it's the trig function that doesn't have the same letter that this thing starts with. So this is the cross product. So it's not the cosine, it's the other one. That would be sine. So what do we have here? Let's look at the case on the left. These are parallel to each other. You can't take a cross product of two things that are parallel, you just get zero. So there is no magnetic force on this current carrying wire because B is parallel to the L vector. The L vector goes in the same direction as the current does, but we assign L as the vector. We don't assign I as the vector because current is a scalar. How about the next one? Here, everything is perpendicular. I think the magnitude of the force is going to be I, which is 2, times L, which is 1.5. So that's 3 times 5. So I'm thinking that FB is going to be 15 newtons. And can we figure out the direction? If we use our pat right-hand rule, we can take our thumb and point it in the direction of the current, and our fingers are going to point in the direction of the field. So we're patting up towards the camera. We could indicate it like so. How about this one? We were told at the beginning that the length of wire that was assumed to be in the field was 1.5 meters. Here, we're not going to get 15 newtons because only the bit of the magnetic field and the current that are perpendicular is going to give us some sort of a non-zero force. Let's do this equation here, ILB sine theta. Now we need to be careful with theta because by definition, theta is the smallest angle between the vectors when their tails are tied together. And you can see that this L vector points in that direction right there. This 35 degrees is not the angle that we want for theta. The angle that we want is this one here, 55 degrees, because that's the angle where the two vectors have their tails tied together. You can see that the 35 is not where the tails are tied together. To find this one, we're going to go I times L times B times the sine of 55. And when we do that, we end up with an answer of 12.3 newtons. And what's that direction? Again, we can use our right-hand rule. The portion of this current that is going toward the top of the page we can ignore, but there is a fraction that's going to the right, and there are the field lines. So again, it's going to be directed toward the camera or out of the page.